Yeah. Okay. So we will do two applications. One is how you can solve ODEs, and the second is how you can solve PDEs. So I think these are two very important applications of using GPU computing, and we will see with simple examples how you can do that. Okay. So what did we do last day? We did a bit of numerical integration. We did matrix vector operations. We did matrix operations, and we did something solving linear equations with something called successive over relaxation. Today we will look at how we can solve ODEs, and we will see at what point parallelization and GPUs come into play. So first of all, yeah, by ODEs I mean equations of this form: x dot, where x can be a vector, it can be a single variable, dot represents the time derivative, let's say, or it could be some other derivative also, but generally we in physics and engineering problems will be having some sort of a time derivative is equals to some function of x itself. So all the quantities on the in this equations are vector quantities, and that is actually important for later on, because we will see why. Anyway, so if we have a simple f of x, like something which is common, it can be integrated analytically. Let's say you have x dot equals to, let's say, x squared or minus x or something which is simple, you can integrate them analytically. But most systems are not simple. Like it can be some nonlinear function. The f can be a nonlinear function. It could have trigonometric functions and exponentials and so on and so forth. And integrating those are difficult. And the other more important point is it could be high dimensional. X could not be a single variable. X could be a vector. Like X could be a vector consisting of some 100 variables. There are systems which are described using 50 variables, 50 state variables, 100 state variables, 10 state variables. So in those scenarios, it is next to impossible to integrate them analytically. Unless they are a very special mathematical form, you will not be able to integrate them analytically. And by integrate, I mean you have to solve the equation and find x as a function of time. That is what I mean by integrate. So in those situations, you have to do a numerical integration. So yeah, and how do we do that? So one of the basic methods is Euler method. And what you do is, if you have that equation, like what I described, x dot is f of x, and now I am discussing it for the most fundamental form where x is the single variable, you can have x of n plus 1 is xn. You evaluate the right hand side at xn and you multiply it with the time step. And you will be given an initial condition, because from basic mathematics you know that to solve a differential equation, ordinary differential equation, you have to be using some sort of an initial condition. You need the value of x at time 0. What we have done here is we have taken the time axis, where generally in a problem your time will be a continuous variable, right? Time will vary continuously from 0 to some final time t. In this case, we have to discretize the time variable into time steps. So let's say you are starting at 0. The next value you will get is at 0. From 0 you will go to delta t. From delta t you will go to 2 delta t, so on and so forth. And you will integrate in steps of delta t from 0 to some final time capital T. And you will be given that x at 0 is some variable. Let's say it is 0.5 or something. So you will put n equals to 0 here first. So you will put x0 as 0.5. You will evaluate the right hand side, that function f, at 0.5, multiply it with delta t, and you will get that x of 1, because you are putting n equals to 0. So yeah. So how do we arrive at this? We arrive at this by expanding that right hand side in Taylor series and ignoring terms of delta t square. So this is the Euler method. So while we will use much more sophisticated methods later on, is this parallelizable? The question is this parallelizable? Can anybody take a guess or give me an answer if this process in any way, if it is parallelizable?
This may not be right, but because n plus 1 requires the nth term, I don't think it's parallelizable in that time direction.
Correct. So
It
you're
might.
absolutely, yeah. It is not parallelizable in what he said. It is in the time direction that you have to have x0 to get x1. You have to have x1 to get x2, so on and so forth. But what sort of parallelization might happen? So I will give you the answer now and we will look at it later. So let's say in physics problems or engineering problems or some other thing, you generally solve a differential equation which has some parameters. Like you might solve dx dt. Dx by dt equals to ax, correct? So that a, this f of x could be a into x. So, and you might need to solve the system for different values of a. In that scenario, you can parallelly solve for a equals to 1, a equals to 2, a equals to 3, so on and so forth. So the problem is not parallelizable in the time direction, as Swarnim said, but if you have to solve the system for different parameter values, which generally you have to study a physical problem or an engineering problem, you generally have to solve a system for different parameter values. So in that scenario, you can solve those parallelly. For A1, the evolution is independent. For A2, the evolution is independent, so on and so forth. So you can solve them parallelly. Now, the standard method which is used all over for most of the problems is the fourth order Runge-Kutta method. It is much more accurate, and so how does this method look? To go from time t to t plus delta t, you do a step like this. So you have to first calculate 4 coefficients k1, k2, k3, k4, and then you will go from xn to xn plus 1 using this formula, where xn plus 1 is xn plus 1/6 k1 plus k4 plus 2 times k2 plus k3, where all these k1, k2, k3, k4 are evaluated using this formula. Now you can see what does these k1, k2, k3 and k4 have. It has the delta t times the function evaluated at xn. So again, do you think this process is in any way parallelizable? It is not, right? Because to calculate k2, you need k1. To calculate k3, you need k2. And to calculate k4, you need k3. So in the Runge-Kutta, fourth order Runge-Kutta method also, you cannot anywhere parallelize the time direction because you need xn to go to xn plus 1. But within the method itself, you cannot parallelize the calculation of all the k values. You cannot parallel between this k1, k2, k3 and k4. So how is this anyway useful? Again, as I said, there are two ways. You might need to solve this problem for many parameter values. In that case, you can parallelize for different parameter values and solve each problem separately. Otherwise, there is another way. What is that other thing? Again, as I said, different parameter values can be computed in parallel, but this is what I will discuss now. If x is sufficiently high dimensional and is of a certain form, the evaluation of f can be parallelized. This one is easy to do. You just run a loop for different parameter values in hash pragma or ACC parallel loop, and you can do that computation in parallel. This one is easy to. The first one is easy to do. What needs to be seen is how you can do it if what you have is that f is sufficiently high dimensional and your x is also sufficiently high dimensional. So we will see this. As an example of this type of system, I will give you the coupled Kuramoto model. This is a very popular model, and it is a high dimensional model, and this is how it looks. The variable here is phi. This is what is called a phase oscillator. Phi is the phase which varies between 0 to 2 pi. Okay. So phi dot is d phi by dt. Omega I is the natural frequency of these phase oscillators. So what is omega I? Omega I is that frequency by which the phasor is rotating in the 0 to 2 pi domain. So you will start and your angular velocity is omega I. And all the omega phi's, all the phase oscillators, all the phi variables are coupled to each other. What is meant by coupled to each other? That phi I not only depends upon phi I as I have shown here, it also depends upon all the other phi j's and the coupling. This is how the interaction comes into the play, that it is of a type of coupling which is given by sine of phi j minus phi I. And you take a summation over all the j's, and j goes from 1 to n. What is n? N is the number of the oscillators, number of the phase oscillators in the system. Similarly, this I also goes from 1 to n. So to solve a system like this, again, we will go back to, we will use Runge-Kutta fourth order method. We will have to do this, and this has to be done for all I. So x n plus 1 will be computed for all I, and this f also will be computed for all I. Okay. Okay, yeah. So now you can understand that all the updates for a single variable of I is independent. So if you have phi I, once you have calculated all the, by the way, this coupling k I have used here is not that k1, k2, k3, k4. I have missed this notation, but this k is the coupling strength. I will tell why it is important a bit later, but this k is not the same as the other k I have used in the previous slide. So yeah, I was saying here, once your k1, k2, k3 and k4 is calculated, all these updates can be done in parallel, number one. Number two, if you see, this function has a summation inside, and as I have said, summations like this can be performed in parallel using something called a reduction. We have seen reduction in previous classes. So what we can do is, we have to evaluate k1, k2, k3, k4 in serial, one after the other. There is no two ways about it. But while evaluating each k, that k1, k2, k3 and k4, we can do that, this summation in parallel. And this form of coupling is not a very special case that I have made up a system which looks like this. This is a form of a mean field coupling, and this is, you will find this across, probably not sine, but different types of mean field coupling you can find across various types of physics and engineering problems. This is a very well established assumption where you assume that different agents or different oscillators or different members of the system are interacting with a mean field of the overall system. And as I had said, this omega I is a natural frequency, and they are sampled from a distribution g of omega. As in, omega is not same for all the oscillators, it varies with each I. So omega 1 might be 0.5, omega 2 might be 0.3, so on and so forth, and it will be taken randomly from a distribution g of omega. The standard result for a system like this is that for a Lorentzian or a Cauchy distribution, which has a form of this type, where g of omega is given by 1 by pi delta over omega square plus delta square, where delta is the scale factor. This is a parameter of the distribution. The synchronization transition, what is synchronization, I will tell you, happens at 2 delta. So you will increase this coupling strength starting from 0. So let's say if this k is 0, so this red term disappears, right? So all the phi values are just phi dot equals to omega I. For k equals to 0, they are uncoupled and they evolve independently of each other. But once you start having some value of k, what happens is the equations become coupled. So the property of this system is that all the phi values start to group together, and that is called synchronization. They start to take the same value, and that sets in once your value of k is equal to or more than 2 delta. So what you can see is if you plot the amount of synchronization in the system, which is defined by an order parameter r which varies between 0 and 1. I will show that equation to you a bit later. I have it in my code. And you vary this value of k from 0 to some positive value, crossing this value 2 delta, where delta is the scale factor of your distribution, you start getting synchronization. So now we will see how does the code look like and how does it work. I think the screen is not visible. Okay, using this example, I will showcase many of the different things we have learned. Yeah, GK, I'll come to this 2 delta. Just let's first go through. Okay, before going through the code, let's do that then. So delta is the parameter which is the scale factor of the distribution of the natural frequencies. What is that? As I have told you, all the frequencies of each oscillator is different. No two oscillators has the same frequency generally. So the distribution from which these frequencies are drawn is parameterized by a parameter called delta. It is called the scale factor, and this controls how wide your distribution is. I hope everybody understands what is meant by a flat or a spread out distribution. Now, if you start increasing the value of the coupling constant k from 0 to a positive number, once you cross 2 delta, that can be shown mathematically. That derivation is not supposed to be discussed here. I am telling you that Kc, the coupling constant at which the oscillators start synchronizing, that is their dynamics starts to look similar, because if your k was 0, all the dynamics was independent. So if you have different initial conditions, you will evolve differently. But once you give a coupling strength k, the dynamic starts to get coupled. In that scenario, if you increase your coupling strength to more than 2 delta, where delta is this parameter over here in your distribution function, you will start to get synchronization. So that is the origin of this 2 delta. This can be mathematically derived, and that is a separate question. But right now we will look at if we are actually able to get this using a normal CPU code and a GPU code, and we will see how fast it solves. Okay. I have defined my system size, that value of n, as 10,000. I am solving for 10,000 oscillators. I have defined my simulation time to be 1,000 time steps. Now, the way I write this code is I create a class, so that before that I will come to the main function before I describe the class. So this is a Kuramoto model. So I have defined the Kuramoto class before. So I create an object of that. I initialize it. I initialize it with this GSL random number generator. Why is that necessary? Because of two things. The first thing is, as I have told you, all the frequencies, the values which are stored in the omega are random. So I have taken a random number generator and I have generated all the distribution of the omegas using a Cauchy distribution or a Lorentzian distribution that I have said before. I have chosen in this case my delta value to be 1.5, that is the delta. Also, I have chosen my phases, the phi's, and I am initializing them between a random number between 0 and 2 pi. This is how you initialize a Cauchy distributed random variable, and this is how you get a random variable whose distribution is flat, and the flat distribution is between 0 and 2 pi. The phases are between 0 and 2 pi. So this is in the initialization function. I have put my dt, my time step, as 0.01. So I will be taking time steps of 0.01 to solve my ODE. And what I have done is I have some data members phi, which stores the value of each phase. This is an array. The t phi is a temporary array which is needed for this computation. Omega I have stored as W here as the natural frequency, and K here is that K, not the coupling strength, but K1, K2, K3 and K4. I will come to that. And there are some other variables also needed. The coupling strength here is sigma, which I had written just capital K in my slide, and R is the order parameter. What is the order parameter? I have calculated here. It takes the exponential, so the function is 1 by n summation j equals to 1 to n e to the power I phi j. So it takes a vector sum of all the phases and taking each component. First I take the cos and the sine. I take the cos of each phase and sine of each phase and add it to some separate variable, and the order parameter is given by 1 by n square root of cos square r plus sine square r. So this is very typical order parameter which is used in the computation of the Kuramoto system. Maybe you are not trying to look at a Kuramoto system, you are trying to look at something else. So in that case, you might also not need to calculate this, but for this system, it is needed to calculate this. So I have written the function. I have initialized my variables using double and float, and these are all, since the system size is n, I have used an array of size n, and the k. Now let's come to this k. Why is it 4 into n? That is because if I go back to my previous slide, how do I go? 1 second, where is it? Yeah. So for each, so this is showed over here, for every state variable I, you have to calculate 4 such values of k. So if there are n variables, n such state variables, you have to calculate 4n of the k variables. So I have now initialized k as 4 times n. I have n number of state variables, and for each state variable I need 4 such values. Okay. Now what I have done here is, this computation will be done in the GPU as I have said. So I have to copy the data. So I am copying this whole data set into the GPU, and I have used that unstructured data directive because this will be called from within a function. So there will be no structured block after this. Therefore, I will be using an unstructured data directive to copy all the data from CPU to GPU. So I am doing a copy in. This represents I am copying in the pointer. So this will copy in the pointer. I am copying in the, I am copying in all the phases. This has to be copied in. Why? Because I am initializing the function outside on the CPU, and also the omega values, the frequencies, those are being initialized in this loop. This is done on the CPU. You might ask me why I am doing this on the CPU. That is because the functions, at least which I have used, this GSL ran Kochi, GSL ran flat, they are not, these are actually from a library called GSL. This library is not compiled for the GPU. You are writing a GPU code, but this is a pre-built library which I am using. Therefore, these functions are not actually compiled for the GPU. So I have to initialize them on the CPU because the functions are defined for CPU execution, and then copy them to the GPU. There are current and those sort of functions available in libraries which can do this directly on the GPU, but I prefer doing them on the CPU because for me it is easier to think of it this way. And also I will be doing this only once. While initializing the system, I will be doing this procedure. I am not doing this multiple times, so it is okay. I will do this once on the CPU and just copy it to the GPU. Apart from that, I have copied in phi, omega and this. So whatever values I have initialized, they have now been transferred to the GPU. Next, I have to create, because there is no need to copy these variables. These are just empty variables which will be updated inside the GPU. So I don't need to copy those values, I just need to create it. So I will just create a variable k of the same size, and I will also create another variable t phi which is here. So I have copied the initialized values and I have created the other two variables, other two arrays as I have needed it. Okay, before I proceed, I will just show you the cleanup function. This is just as a bookkeeping so that there is no memory leak. So similarly, after the simulation is finished, if you are going to do this for many parameter values, you will create many objects of the same type. So if you actually don't delete the data from the GPU memory, you may end up causing a memory leak. So delete both on GPU and CPU is important. So there is a cleanup function. All right. Now here comes the RK4 method. In this RK4 method, what am I doing? I am taking a time step to go from t to t plus delta t. So this is step forward. This is step forward RK4 for one time step delta t or dt whose value is 0.01. I am taking a time step of 0.01 and going from t to t plus dt. Sorry. Okay. Now let us see how we are doing that. So let us go back to the RK4 algorithm. What you see here is K1 is calculated f of xn. K2 is calculated xn plus 0.5 K1. K3 is calculated xn plus 0.5 K2. And K4 is calculated xn plus 0.3 plus just K3. Okay. Now, what you see here is we have to preserve the value of xn. Otherwise, if you change the value of xn somehow, there will be an issue. So you have to preserve the value of xn because xn is needed here to perform the update. Therefore, what I am doing here is, I will put this to the side. Okay, yeah. So what I am doing here is, I am preserving the value of xn, I am copying it to t phi, so that I can modify t phi and not only phi. By that what happens? I am preserving the value in phi so that I can use it in the update step. What is the update step? This is the update step over here. Okay. Now there are four values, K1, K2, K3, K4. So I run a loop which goes from 0 to less than 4. Basically K0, K1, K2, K3. It is the same thing. Now within for each value of k, so you see this for loop does not have a hash pragma on top of it. This for loop needs to run in series so that it goes K1, K2, K3 and K4. Now what we do is, For each value of k, I have to evaluate this function. So what is this function for Kuramoto model? It is just sine of phi j minus phi I multiplied by k over n into omega I. So I am doing the same thing. I am storing this phi I from t phi. I have stored it and I am creating a sum. What is this sum doing? It is accumulating using a reduction all the sin f t phi j minus phi I. After that, what is the next step? I have to store it in k1. But k1 is not only the summation, I have to add the omega I and multiply by dt as I have shown here. So I am multiplying by dt and I am adding omega I. So this does it for the first value of k. Now you might say that what is this index here? So as I had said, we have to do for every variable n for every value of k. But the k has to go in series. So you could have done it using a matrix, but as we had seen the previous day, using a matrix is slow. So if you can flatten out the system, you will be able to do it faster, because a flattened out matrix will be stored in contiguous side by side memory location. Okay, so I am using the same concept I had used the previous day. So if I had k in bracket k comma I, that will just become k into n plus I, and I have stored that. Now there is a if else statement here. Why? Because for the next step, the value of xn has to be updated. So I am seeing if k is less than equal to I, it will be 0.5, 0.5, 0.5, or it will be 1.0, because in this case it is 1.0, and I am updating t phi. Okay, so in this way it is going in the loop. It will do for k0, k1, k2, k3, k4. Okay, and how am I getting this t phi? See, there is phi I, which is xn, because in my problem x is phi, and I am adding 0.5. Val stores this value, either it is 0.5 or it is 1, and that into the value of k, k1, k2, k3, k4, which is coming from here. So I am updating t phi in that way, and this will happen for k equals to 0, k equals to 1, k equals to 2, k equals to 3, k equals up to k equals to 3, sorry. Now once all my k values are ready, so all my values are ready, I have to execute this. Again, this can be performed in parallel. As I have said, once all your k values are ready, you can perform xn plus 1 xn by 1 by 6 for each I independently. So again, there is a parallel loop here. I am updating phi I equals to phi I plus 1 by 6th of this expression. So k1, k4, k2, k3. So you have k0, k3, k1, k2, because in the C programming notation it begins with 0. So I have used that. But here what is k0, what is k1 is here k0, what is k4 is k3, so on and so forth. So this is what I have used. Okay, now let us see what is before this. Again, since I have already copied the data here, I have to tell the compiler that data is already present. Okay, so this function, what this function will do is it will take your system from t equals to t equals to t plus delta t. And what is this bound phase function? This function is here because, again, this is a mathematical consideration. It will work without this as well. So that since we are on a circular ring between 0 to 2 pi, if it goes beyond 2 pi, it will circle back to 0. So that is what bound phase has implemented. That is a simple logic. If you go beyond 2 pi, you have to go to 0. So what am I doing here? And okay, there is another function here, set coupling to constant. This coupling the constant k, which I have put here, is sigma for me here because of the notation, and I will update this coupling constant in every step of the simulation. So I have set a function coupling constant, set coupling constant, where I set the value and I update the value on the GPU, because this sigma will be used over here inside the loop. So this value needs to be present on the GPU. Okay, now we will look at the main function. I will vary sigma between 0 and 6. So I will vary the coupling strength. I have told you that the initialization has been done for the frequencies using a scale factor of 1.5. So my transition point is at 3, at near about 3. So we do a parameter sweep in steps of 0.01 from sigma equals to 0 to sigma equals to 6. We set the value of the coupling constant sigma. When I call this function, it will set the value and copy that value to the GPU, as I have done here. It will copy the value to the GPU. Then I will run a time loop. Again, as we have said, time evolution is not parallel. We have to do in serial, so therefore there is no hash pragma OMP or ACC parallel for or before this loop. And I am doing the step forward function t number of time. And after that, I am calculating the order parameter, which will tell me if there is synchronization, and we are printing it. So we will see how it goes with this one. Let us first compile this. Okay, this is compiling for multi-core. Let us run this. So it will show you the output here. I will tell what it is. I am also computing the time, how much time it takes to do t time steps for a particular value of sigma. So that will show up in this one. So I can show you how much time it is taking for every value of sigma. So I think it will take around 24 seconds. Okay. So it for sigma equals to 0, it took around the order parameter value I have printed here, s dot r, I have printed here, and it has taken around 24 seconds. Let us execute this on the GPU and you will see how fast it is. Oh, okay. Yeah. So this is now the compiler output. You will see it has generated loops in many positions, that parallel GPU code in many of the positions where I have put that hash pragma ACC parallel loop and all. And it has generated the copy in as I need in line number 70. Let's see what if that is there in line 70. Yeah. You see it has generated all the copy in and everything. Okay, now let's run this. Yeah. You see, what was taking 24 seconds on the parallel CPU is taking 0.9 second on the GPU. You can imagine how fast this is if you compare between the CPU and the GPU. It is taking around 1 second, 0.9 second, so on and so forth. That time will vary, but yeah. So once you go to sigma around 3, you will see this value starts to become non-zero. Yeah. You see, right after 3, this value starts increasing. It becomes 0.16, 0.2, 0.3, 0.47, 0.5, so on and so forth. So that is also verified that the system starts synchronizing right after k equals to 3. On this column, I am plotting the value of k. and this I am plotting the order parameter. So this is showing me that right after the value 3 is passed over here, I am starting to see synchronization. 3.1 is 0.04 and from 3.2 it starts to increase. The main important thing here is what took 24 seconds for each parameter value is taking just 1 second or 0.9 second here. That is a massive speed up, and this is only possible because GPU is there. Anybody has any questions? This is a very important example, and actually I use this code for my own research work. So this is code which I have developed. Anybody has any questions regarding the ODE solving part? See, for your system, it might not be sine, it might be some different function, but if you have a system which is coupled in this mean field format, which I am guessing many systems are, you can use the same procedure. You can have a parallelization of the right hand side and you can run the code on the GPU. It might not be the Kuramoto model, it can be something else. Some people work in neuroscience, let's say. They simulate the brain in certain scenarios and they will simulate millions of neurons. And then if you have a neuron model, which is let's say described by a Hodgkin-Huxley model or things like that, I can show you the example of that maybe. Let's see, neuron model, Hodgkin-Huxley. It is given by a differential equation of this type, and you can have it in a network where there are many such neurons. So I'll show you this paper. So if any one of you are working in this sort of a domain, you can use this. So I think they have a coupling term here, network design. Yeah, you see this. In this paper, they have a coupling term of this form. They don't have a sign, they just have Vj minus Vi, but the theory, the procedure of parallelizing will be the same. So this is quite a general way of doing a GPU parallelization for solving ODEs. The other is you could do for different parameters. Like I could do in parallel for one value of k, for other value of k, and so on and so forth. That would be the other way of doing it. Okay, so this is all about ODEs. How you can, I am showing you an example for that how you can parallelize solving a ODE. Similarly, a big portion of physical problems are not only described by ODEs but PDEs, where there is not only a single state variable, the state is dependent on one or more variables. I will go to presentation. So it's a partial differential equation. Let's say you have a string which is vibrating. The displacement of the string is dependent not only on time but also on the position of the string. That is where you solve the wave equation. If you are solving for the temperature of a rod, let's say you have a metal rod and you are heating it at both ends, or you are keeping both ends at some temperature, and you want to find, given an initial condition, how does the heat flow, how does the temperature change in the rod. So that type of situation you will have to solve a heat equation. These are all PDEs, and for such a case you need to give it the initial condition and the boundary condition. And PDEs, such differential equation, will have derivatives, and these have to be discretized using what are called the finite difference schemes. So let us look at the heat equation because this is the simplest one. So it has two variables, as I said, the temperature depends on time and space. The equation is del u del t is alpha times del 2u del x squared. What is u? U is the temperature at position x at time t. and alpha is some constant. So the system is governed by this equation. So how do we solve this? This particular equation can be easily solved analytically, but for the example we are going to do this numerically. So we will look at what are called finite difference schemes. So you must remember the definition of the limit what you had done in I think school or college, and this looks similar, isn't it? So del u del t is t plus delta t minus u of x of t divided by delta t. This looks very much like the definition of the derivative. You can also get this by expanding u at x comma t plus delta t in a Taylor series and truncating it. To get the double derivative, what you have to do is, by the way, I am showing the double derivative for time. So delta subscript t means del u del t. So this del u del t is this. And del double t means you are taking the second derivative, the double derivative. So over here, the double derivative is with respect to space, but the format will be the same. You just have to replace this del double tu with del double xu. So the double derivative looks like this in the finite difference schema. Again, how do you get this? You expand u of x t plus delta t and u of x t minus delta t in Taylor series. You subtract both of them. You truncate at order t cube term and you subtract both of them. In that way, sorry, you don't subtract, you add. You add both of them and you will end up with this. I suppose it is easy to obtain this. It is not that difficult. You just have to write down the Taylor series. Okay. So again, we will have the same finite difference scheme for the space derivative as well. So in the explicit form, why am I telling it is the explicit form? I will tell you that del u del t I have replaced by this, that which looks almost like the school definition of a limit, alpha times, and the second derivative over here is, as I said, that was defined for time. So that was t plus delta t and t minus delta t here. But for this case, you have to do x plus delta x and x minus delta x and divide by delta x squared. So delta t and delta x is your time and space resolution. How fine you are going to solve that? Okay, why am I calling this the explicit form? This is called an explicit form because the right hand side, you have defined it, or we have taken it, the finite difference scheme. This is x plus delta x, x and x minus delta x is fine. We could have anyway defined this for t plus delta t, t plus delta t, t plus delta t here in each of these terms. So what would happen is, like for this, what happens is, if you now denote u of x comma t, you discretize the x direction using some index I and you discretize the time direction using some index n. So x is I into delta x and t is n into delta t, that way. What happens is u of I n plus 1, because t plus delta t is here, so u of I n plus 1 depends on only u value at n, the value of u at time n. It will depend of I plus 1, I and I minus 1, but it only depends, and I have this constant I have taken here, this delta t, but it generally depends on n only. On the right hand side there is only n, and on the left hand side there is n plus 1. So this is an explicit form. You know the right hand side fully and you can get the left hand side from it. In certain scenarios, and people mostly do that, I have not done here for sake of simplicity, but people generally do what is, they generally define the right hand side in terms of t plus 1, actually t plus delta t. So that will result in n plus 1 appearing on the right hand side. So what it becomes is a implicit equation. So it does not remain a equation which looks like this, and it becomes a set of linear equations which you have to solve. And for solving that, there are other routines and it becomes a bit complicated. But for the simplest example, this is fine. The right hand side is only dependent on n, and left hand side involves n plus 1. Again, if you see, the same properties of the ODE follows, that you need the value at n to get n plus 1. But similarly to the ODE, you can update for different values of I in parallel for particular value of n. Let's say you are calculating u of 6. For that, you need all the values of u of 5. U superscript 5 you need. But for the subscript, u1 can be updated independently of u2, which can be independently updated of u3, because this I index is independent of each other. So in that way, you can also parallelize this process, and it can be parallelized for all I. Now you might ask why people would do that n plus 1 thing on the right hand side and get an implicit form. That is because this explicit form is not very stable. You have to choose very particular values of delta t and delta x so that the solutions don't diverge. To prevent that, people use that implicit form, which can be shown to be stable. But implementing that for a simple example is a bit difficult, so I am skipping, not doing that. I am doing for the explicit form, but that can also be done. And once you have a set of linear equations, either you can call cuBLAS and other BLAS libraries, or you can solve it yourself using some sort of a solver. Like previous day we had solved linear equations in some way. This set of linear equations, if you end up with n plus 1 on the right hand side also, you can solve it treating the system as a set of linear equations. But for now, we will do the explicit form and we will see how this can be parallelized. Okay, let's go to the code then. Okay, so we are solving the heat equation. The length of the rod for which I am solving the heat equation, I have taken to be 1 unit. I am dividing that domain into 200 smaller steps that will now decide how many values of I will get. I will run from 0 to n plus 1, 0 to n, and I will solve for some time duration. As I have said before, I need to give the initial conditions. This gives you the initial condition of the rod, like what was the initial temperature profile. Okay, the other assumption which I am doing here is, in this problem, the boundary conditions what I have taken is, which I have not mentioned here, but the boundary conditions what I have taken is the both ends of the rod from x equals to 0 to x equals to L is held at 0 degree. Okay, that is held at 0. So, yeah, so if you see, if you plug in 0 here and if you plug in L here, you will get that sort of a thing. All right. Now, then it is very simple actually. Once you have the explicit form ready, it is very simple. What you do is, you again define a u and a tu. Why t temporary? By t I mean temporary u is needed because I will have to update all the values of I in parallel. So you do it in a new array tu and you then copy the array back into the value of u. You initialize the system for this. I am using that initialization system whatever I have used, and for every value of x will be like the index into my space resolution, whichever is dx, and I am storing tu to be 0, and I am calculating this constant, whereas this constant I will mark it as r, and it is just, yeah, delta x squared power of a square. Okay, sorry, this I think I have made a mistake. This is not alpha here. This is stored as alpha squared. I think I made a notation error. But anyway, yeah, this should be alpha squared, not alpha. I will correct this before I upload the slides. Okay, so a squared dx by dx squared. this is squared here, this is dt here, and this will be alpha squared. I have now copied the data. I am doing a copy in for u dx. Dx is my space resolution, dt is my time resolution, and tu is the temporary. You will see that time resolution I have taken in a special form. This is again due to the stability issues of the explicit form. I have to take it at least this way. Otherwise, this will diverge. So there is a reason why I am taking this in this way. And then what I have done, I am doing a parallel for. For here, I have implemented it in CPU. I have implemented it using OpenMP. So let's do it using ACC. So this loop is doing the explicit time step. The equation 12 is being done using this loop, that u of n plus 1, which is tu, is r into, this is r, and this can be simplified into this form. So you will take r into this plus this, and then r into 1 minus 2r it will become, because this r will multiply with 2 here, and you have ui of n. So you have ui into 1 minus 2r. So you are creating this u of I into n, where at time n plus 1. But then this has to be copied back, because this is an iterative process. This has to be copied back into u of I, because for the next step I need that. So here I am copying it. And after every time I am printing to the terminal, I will put it to file, the time, the position, and the temperature. Let's see how it looks once I run it. See, it ran immediately, because I have actually, because if you take a very large value of n, this will run very slowly, which I have kept for GPU part. But in this case, just to show you how the solution looks, I am running it on the CPU for small value. I will now show you the plot of it. I will go into GNU plot, and let's see how it looks. Yes. So the initial condition was taken to be oscillatory, that the temperature profile is like this. If you can see, for t equals to 0, the temperature profile was oscillatory. This is the x-axis, this is the time axis, and the z-axis is your temperature or your value of u. So you see that it is some sort of oscillatory behavior is there, and then since the ends are held at 0 degree, the temperature profile settles down and it becomes a uniformly having uniform temperature almost. See, it looks like this from this side. And you can see that if there are oscillations here, those oscillations are not here anymore. This is the time axis, this is the x-axis. Okay, since we now know that the solution is more or less okay, we will run it on the GPU and see how fast it runs. We will use a larger system size for that. Okay, now I have saved it. Let's compile it for the GPU then. Where is it? Yeah, GC++ heat 1D ratio, and I am compiling it for the GPU. Yes. So this, if you remember, is somewhat like that example we had done before, that we should actually copy the data before the time loop. If we don't copy it, like if I don't give this statement over here, what will happen is it will put that data copy inside my time loop and create an issue. Yeah, you see it is generating the data copy inside the time loop, which is not good. It will become very slow. So we are doing that copy outside the time loop, because to do the time iteration, we don't need to copy the data to the GPU, to the CPU, sorry. And okay, since we are not going to print it, we'll just comment out this line. We will see how fast or how slow it executes. So let's first execute it on the, maybe on the CPU. Yeah, it will be just this. PA equals to multi-core. Minfo equals to Excel. Okay, let's run it on this one. It will take a bit of time to run. Okay, I'll just put time in front of it so that we can count how much time it is taking. Okay, I know I am going beyond time, so this is the last class. So this is the last example I will do. I think it should be okay. Yes, so we see that it has taken around 12 seconds or 11.97 seconds, something like that, to execute it on the CPU. Now let's see if it is faster on the GPU. It might not be, because who knows, let's see. Let me see if it is actually executing on the GPU. Close the slides. If it is not faster, I'll have to troubleshoot it and see. I think it is taking around 35 seconds. Let's see why it is that. Could it be because the system size is small? Because for smaller system sizes, this process of starting the GPU threads every time and all, that will take too much time. So let us maybe check using a bigger system size. And have I compiled it correctly? CC native -o fast minfo Excel and 20,000 1024. Okay, let's see. Let us make it just vector. Sometimes that could be the issue. Okay, but before doing 20,000, let us check with this one. It is executing on the GPU all right, but let's see how much time it is taking. It's still taking around 35 seconds. So let's just change the vector length and see how much it is actually doing. Again, these things require a bit of tuning, and yeah. And the other issue with this type of explicit form is that since the work is not that compute intensive, for every I it is only updating up to a certain step. It might be that it is not enough to just, it does not need a GPU acceleration at all, but the concept that way is clear, that it is parallelizable. So let's see if it is better this way. Might be that it needs a longer time evolution to work also. Maybe I can put 10 seconds here. It is taking around 58 seconds. If I remove that vector, let's put vector back. Anyway, the thing is, it should be working, but I'll have to see why it is slow here. But overall, the thing is, for this type of PDEs, you can explicitly convert it to a algebraic form, iterative form in this way, and then you can run a loop like this, and you have to do the data copy operations and all. I think the reason this is running slow is because the amount of work being done in the loop region is not that much. So that could be one of the reasons it is running slow. And it has to launch the GPU kernel every time it is inside the time, inside this loop, in this time loop. So that could be one of the reasons, but I'll have to check this up. But I think apart from this, the serial solution you have seen, it actually works. And if you have a more complicated PDE or something, that would, I think, benefit from the GPU execution. I will just see why this is not working faster. I'll check with vector length 1024. Should take around 30 seconds as I saw the last time. Anyway, but apart from the acceleration part, the parallelization part, I think, is easy to understand for this, isn't it? Does anyone have any questions regarding the parallelization part? See, this is executing on the GPU, I can see that, but I think there is some issue regarding this loop, because this is actually not that of a compute intensive loop. It is just doing a vector operation. So I'll have to see whether this is the reason why it is slow. But I suppose you have seen in the case of the ODE, that is the code which I'm very comfortable in. These are codes I've written recently, but that ODE code is what I use for my own research. That is very much optimized, and that you have seen is actually very useful in terms of speed up. Something which is taking 24 seconds will take just 1 second to execute in the GPU. I'll have to check this up, but I will share the slides, so I think you can try it out. Apart from this, does anyone have any questions, like regarding the ODE and PDE thing which we covered today, or whatever we had covered before? Or do you have any problem which you want to parallelize yourself and maybe you want to discuss? Do you have any questions? We can discuss it now. Okay. So if there are questions, you can always email me. That email address is there on that course page. And I will share, I think I have not shared the recordings of the previous 2 days. I will share those and the today's slide as well, so that it is available to you on the course page. Okay. And all right, if there are, I'll then just stop the recording for now then.